Welcome to the numerical analysis course. In this lecture, we are going to study about computing eigenvalues using numerical analysis technique. Eigenvalue is a value that is defined for a square matrix A, and actually we assign two. For a square matrix, we derive two quantities, eigenvalue and eigenvector. Eigenvector is a vector that is associated with a matrix A such that any transformation applied using that matrix is represented by a change of by a scalar value. This means that let's try to understand this further with the help of this mathematical expression, that given this matrix, this vector is an eigenvector for this, and if this is an eigenvector, this transformation is actually a transformation, it's a linear transformation applied on a square matrix A times this x should yield lambda as a constant value, that is the eigenvalue for this matrix, times the same eigenvector. This means that if it is a square matrix, suppose A is a square matrix of size 2 cross 2 and this x is a matrix as a vector of size 2 cross 1, this multiplication will result in a vector that is of size 2 cross 1. This lambda is a constant multiplied with it's a constant 1 cross 1 multiplied by a 2 cross 1 multiplied with a 2 cross 1. So this 1 cross 1 is a constant value. It is multiplied by each and every element of this vector, and this also gives us a vector of size 2 cross 1, 2 times 1. So the transformation on the left side and this multiplication on the right side, they both produce this 2 cross 1 times. If this matrix is a 2 cross 2 and this x is a 2 cross 1 size matrix, the results are 2 cross 1 on both sides, right? And they are the same, but they are not the same if this x is not an eigenvector and lambda is not an eigenvalue. This transformation is true only if x is an eigenvector and lambda is an eigenvalue. So this transformation of the matrix A using eigenvector, it results in the same eigenvector multiplied with a constant value lambda. So this is the speciality of an eigenvector and eigenvalue, and eigenvectors and eigenvalues are used at several different places in electrical engineering, computer science, biomedical engineering, etc. So it's a very important transformation, that this transformation is equal to the same vector times a constant value. It's a very important expression. If we work further with this expression and we take this lambda times x to the left hand side of the equation, this becomes minus lambda times x is equal to 0. And if we take x as constant, the thing that is left is A minus lambda times I. This I is the identity matrix. For a 2 cross 2 matrix, this is like 1 0 0 1, where we have 1s in the diagonal. Identity matrix, we studied identity matrix in school and colleges. For a 3 cross 3 matrix, it is like this 1 0 0 0 1 0 0 0 1. And for a 4 cross 4 matrix, is also it will have 1s in the diagonal and zeros at all other places. Right, so since we are subtracting something from a matrix, from an n cross n matrix, so we have to multiply this lambda. Lambda is a constant value. We cannot subtract a constant value from a matrix n cross n, 2 cross 2, 3 cross 3 or 4 cross 4 matrix. So we have to multiply this with a constant, with an identity matrix like this. Right, so if this is 0, this means that this is 0, x is 0, or we can say this A minus lambda I, the determinant of this is 0. Right, to check whether since x is not 0, x isn't 0, therefore it has to be 0. This means the determinant is 0. Right, A minus lambda I, let's compute A minus lambda I first, and then we'll compute its determinant and we'll put it equal to 0 to form the characteristic equation. The equation that we compute using this expression, we call it characteristic equation. We are going to study soon. Right. A minus lambda I is a, suppose we assume a 2 cross 2 matrix for simplicity, a1 1 a1 2 a2 1 a2 2 minus lambda times I, where I is 1 0 0 1. So if you multiply a constant with a matrix, that constant is multiplied with each and every element of the matrix. We already know this. It becomes lambda 0 times lambda is 0, 0 times lambda is 0, lambda times 1 is lambda. So if we subtract, this means we can subtract two matrices only if they are of the same size and elements on the corresponding positions are subtracted. a1 2 minus 0, a2 1 minus 0, a2 2 minus lambda. That's all. A minus lambda I. And further, we have to put it in equation number 1. A minus lambda I. Let's plug that a minus lambda I in equation number 1 to find the characteristic equation and some very interesting results. Right. So a minus lambda I is this one. A1 1 minus lambda 0. Oh, not 0, it's a1 2, a2 1, and a2 2 minus lambda. So this is the matrix we have, and now we're going to plug it in equation number 1 and we'll put it equal to 0. A minus lambda I is determinant. So determinant of this would be a1 1, this multiplied by this, minus this multiplied by this. We studied this in school. A minus 1 1 minus lambda times a2 2 minus lambda minus a1 2 times a2 1. So this is a1 1 a2 2 minus lambda times a1 1 minus lambda times a2 2 plus lambda squared minus a1 2 a2 1 is equal to a 0. So this equation is equal to a 0. Right. And then we have lambda squared, and let's collect the coefficients of lambda, minus a1 1 plus a2 2 times lambda plus a1 1 a2 2 minus a1 2 a2 1 is equal to 0. Right. Now we have gathered the coefficients of lambda squared and lambda. This is lambda squared. Right. And we know this is a1 1 plus a1 2. Let me write matrix A once again so that we can see what is this. A1 1 plus a2 2, a1 1 plus a2 2. A1 1 plus a2 2 is actually the trace of matrix A. Trace is the sum of the elements along the primary, the main diagonal. And let's see what is this. A1 1 a2 2 minus a2 2 a2 1. Right. If we write determinant of A, matrix A, that would be a1 1 a2 2 minus a2 1 a1 2, or a1 2 a2 1. So let's see, these two are exactly the same. This means that the characteristic equation for a 2 cross 2 matrix can straightaway be written as the characteristic equation to compute eigenvalues of a given 2 cross 2 matrix can straightaway be written as lambda squared minus trace of A times lambda, or lambda times trace of A, plus determinant of A is equal to 0. This is the general characteristic equation to find the eigenvalues lambdas. In fact, there will be 2 eigenvalues for 2 cross 2 matrix. To find eigenvalues lambdas, it's an equation to to find lambda's eigenvalues for a given matrix A. Let's solve it further with the help of an example. I have a matrix A given to B. A is 1, 4, 2, 3. Right, let's find its eigenvalues straight away using this equation. Lambda squared minus trace of A. Trace of A would be the sum of values along the main diagonal, 1 plus 3 be 4, minus 4 times lambda plus the determinant of A. Determinant of A would be 1 times 3, 3 minus 2 times 4, 2 fours are 8. 3 minus 8 is minus 5. So this is minus 5 is equal to 0. So lambda squared minus 4 lambda minus 5 is equal to 0. And now we can factorize this quadratic equation, or we can apply quadratic formula to find the values of lambda. Two values of lambda. Lambda squared minus, we can write it at minus 5 lambda plus lambda minus 5, or we can just plug it in the quadratic formula. Lambda times lambda minus 5 plus 1 times lambda minus 5 is equal to 0, or lambda minus 5 is equal to 0 means lambda is equal to 5, or lambda plus 1 is equal to 0, this means lambda is equal to minus 1. So using this simple equation, characteristic equation, we can straight away compute the two eigenvalues for a given matrix, for a given 2 cross 2 matrix. In the next lecture, we will use our derivation. We'll derive a similar expression that we did here to find the characteristic equation, to find eigenvalues of a 3 cross 3 matrix. Right, that's all for this. Thank you.